Welcome to another deep dive, everybody. And this time, we're taking a look at how we see the world. Literally.
Literally.
Today, we're diving deep into the physics of thin lenses
Ooh, thin lenses.
with an educational resource as our guide.
Nice.
Think interactive simulations and all that jazz.
All right.
We're going to cut through the textbook stuff, though, don't worry.
Yeah.
And we'll pull out the most interesting insights for you. So by the end of this, you'll know how lenses shape our view, from the camera you have in your pocket to, well, your own eyes.
It really is amazing how something as simple as like a curved piece of glass can have such a profound impact,
Totally.
on our understanding of the universe.
I know, it's crazy. Okay, let's jump right into it. Let's start with something I always thought was really neat, the thin lens equation. It's this deceptively simple equation that can predict where an image will form
Yeah, that's right.
based on just a few factors.
It's 1u plus 1v equals 1f,
Okay, 1 over u plus 1 over v equals 1 over f.
where u represents the distance of the object from the lens, right? V is the distance of the image from the lens, and
Yeah.
f is the focal length.
Okay, so I think I understand u and v. Those are distances. But what exactly is focal length?
Yeah, good question.
Is it like a measure of how much a lens, like, bends light?
You're exactly right. Yeah. Focal length tells you how strongly a lens converges or diverges light.
Right.
So shorter focal length means the lens bends the light more sharply.
Gotcha.
And what's really fascinating is that if you know the focal length and you know the object's distance, you can calculate exactly where the image will appear
Wow.
and even how large it will be.
So a simple ratio of distances, that's all it takes to know all of that.
Yeah.
It feels like a shortcut to understanding how images are formed.
It is. It is. I mean,
Yeah.
that's the beauty of physics, right? You get these simple equations that can actually reveal fundamental relationships.
Yeah.
Of course, the thin lens equation has limitations, right?
Yeah.
For example, we're assuming that the lens is infinitely thin, that it's in air, things like that. But it's a surprisingly powerful tool for its simplicity.
So we have this equation, this thin lens equation, but lenses come in different flavors, right?
Yeah, definitely.
So what are the main types we're dealing with here?
We primarily have two types, converging and diverging lenses.
Okay.
Think of converging lenses as those magnifying glasses you might have played with as a kid.
Yeah.
They're thicker in the middle,
Okay.
and they bend light inwards to a focal point.
Thicker in the middle, bends light inwards. Okay, makes sense.
Yeah.
But how does that translate to real-world applications? It's not like we're running around using magnifying glasses to examine everything, right?
Well, you might be surprised. Converging lenses, they're everywhere, actually. For instance, how about telescopes?
Yeah.
They use converging lenses to focus the light from distant stars.
Right.
So you're bringing the universe right to your eye.
Wow. So it's the same principle behind a simple magnifying glass is used to observe galaxies millions of light years away.
Yeah.
That's incredible.
Exactly. And, closer to home, our own eyes actually use converging lenses to focus light onto our retinas. That's how we see the world around us.
Wow.
And cameras,
Of course.
they use converging lenses as well.
Wait, so my eye, a telescope, and my phone's camera,
All the same.
all based on the same physics of converging lenses.
Pretty much, yeah.
That's mind-blowing.
It really highlights the fundamental nature of these principles, right?
Yeah.
The specifics, the applications, they might differ,
Right.
but the underlying physics, it's the same.
That's so cool.
And the list goes on. We got photocopiers, overhead projectors, spotlights,
Wow.
all using converging lenses.
Converging lenses are like the workhorse of the optics world.
It seems like it, right? Yeah.
What about diverging lenses?
Right.
The ones that are thinner in the middle, what do they do?
Right. Yeah. They have their own roles to play.
Okay.
Although, the source doesn't delve too deep into those,
Okay.
but they spread light outwards, making things appear smaller.
That makes me wonder why we hear so much more about converging lenses then.
Yeah.
Are diverging lenses less useful in everyday life?
That's a great question and something worth considering, right?
Yeah.
I mean, maybe it's because converging lenses can create those real projectable images, like in a movie theater.
Right.
But it is curious that diverging lenses aren't mentioned as frequently.
Yeah. Makes you want to investigate further. Now, we've talked about how lenses bend light.
Right.
But how do we know how much bigger or smaller an image will be?
Yeah, good point. Well, that's where magnification comes in.
Magnification, I
So
see.
magnification is essentially, it's a ratio, and it tells us how much larger or smaller an image is compared to the original object.
Okay, how do we calculate that?
It's another really simple formula, actually.
Okay.
Magnification, or M, is equal to negative V over U.
Negative V over U.
So those distances we talked about
Oh,
earlier,
right, U and V, yeah.
well, the ratio of those distances will give you magnification.
Okay.
So if the image distance, V, is larger than the object distance,
Right.
the image will be magnified. And if it's smaller, the image will be reduced.
Okay.
And that negative sign in the formula,
Yeah.
that tells you whether the image is flipped upside down or not.
Oh, like when you hold a magnifying glass too close to something and it looks upside down.
Exactly. Exactly. And, here's something that I found really interesting from the source. It mentions that you can actually calculate magnification in another way
Okay.
by comparing the height of the image to the height of the object.
Oh, interesting. So it's like two ways to get the same answer.
It's two sides of the same coin.
Two sides of the same coin. I like that.
Yeah. So it's all connected, right?
Yeah.
You got the distances, the sizes, and even whether the image is flipped.
It's all starting to click.
Yeah.
Yeah.
Awesome.
It's really cool.
Speaking of making sense of things, have you ever wondered how we actually visualize the path of light as it goes through a lens?
Yeah. I have to admit, trying to picture those light rays like bending and converging, it can get a little tricky in my head.
Yeah, well, physicists have a great tool for that. Ray diagrams. They're like visual blueprints.
Ray diagram.
Yeah, they're like visual blueprints for understanding light's journey through a lens.
Interesting. Okay, so tell me how they work.
So they're based on the idea that light travels in straight lines,
Right.
unless it's, bent by something like a lens. So ray diagrams, they use a few key rays to help us predict where the image is going to form and what it'll look like.
Okay, so what are these key rays that we're drawing? I'm picturing like light just shooting off in all directions from an object.
Well, we can simplify it down to three principal rays.
Okay.
The first one travels parallel to the lens's axis,
Okay.
and then it bends through the focal point on the other side.
So it starts parallel and then takes a detour through the focal point. Okay, I got that.
Yeah. What about the second ray?
Second ray.
That's the easiest one. It goes straight through the center of the lens, doesn't bend at all.
Okay, so no bending, just straight through the middle. Easy enough.
Okay.
All right, third ray.
Third ray travels through the focal point on the object's side, and then it emerges parallel to the axis after passing through the lens.
So it's like the first ray in reverse.
Exactly.
Starts at the focal point and then ends up parallel.
Precisely. And here's the really cool part. The point where all three of these rays intersect,
Yeah.
that's where the image forms.
So wait, by drawing these three lines, we can figure out where the image will be
Yeah.
and how big it will be.
Yep.
That's incredible.
And the best part is once you understand the rules of how light bends through a lens,
Yeah.
these ray diagrams become pretty predictable. You could just sketch them yourself and get a real feel for how images are formed.
I'm starting to feel like a lens detective.
Right.
Okay, so we can use the thin lens equation to calculate the distance,
Yeah.
magnification to figure out the image size,
Yeah.
and ray diagrams to actually visualize it all.
Yeah.
It's all coming together.
There you go. That's the beauty of physics, right?
It is.
All these seemingly separate concepts, they're deeply interconnected.
Yeah.
And we've only just scratched the surface.
I can't wait to dive deeper. But let's take a minute here. Let all this sink in for a second.
Yeah, good idea.
Yeah.
We'll be back and we'll continue exploring this world of lenses. We'll uncover some more interesting insights for you.
Sounds good. All right, welcome back to our lens adventure. I'm excited to keep bending some light and delve deeper into these lenses.
Yeah, me too.
We've talked about converging and diverging lenses,
Right.
equations,
Right, yeah.
and even those ray diagrams.
Yeah.
But I'm sure there's more to uncover, right?
Oh, definitely. There's always more to explore, isn't there? When we were talking about focal length earlier,
Yep.
it got me thinking about something that the source mentioned. It talked about that very point where light begins to diverge.
Oh, yeah. It said something about the focal length being the distance from the lens to the point where the light starts spreading out when the object's really far away.
Like practically at infinity.
Yeah, at infinity.
And it got me thinking, that definition, isn't it kind of hinting at like the real physics behind why lenses work the way they do?
Okay, yeah.
It's as if the shape of the lens and what it's made of that kind of dictates that specific point where light either converges or diverges.
So it's not just about like bending light,
Right, yeah,
but controlling where that bending happens.
precisely. And that control, that's what allows us to create all sorts of amazing optical effects.
Yeah.
Think about it. Telescopes that can see across vast distances,
Right.
microscopes that let you see the tiniest details of the world around you.
Yeah, it's really crazy when you think about it like
Yes,
that.
it is.
You know what? Before this deep dive, I never really thought about um, how my glasses actually worked.
Right.
Now I'm wondering, like, do my glasses have a specific focal length that's correcting my vision?
Probably, yeah.
It's like all this knowledge makes these everyday objects more fascinating.
That's the power of understanding, right? These
Yeah.
basic principles. It just opens up a whole new way of seeing the world, literally.
Yeah.
You start to notice these principles in action everywhere.
Yeah, it's really neat. It also makes me think about diverging lenses again. We talked about how they spread light out,
Right, yeah.
but do they also have focal points?
They do, but it's a bit different. Converging lenses, they have a real focal point
Right.
where the light actually comes together.
Right.
But diverging lenses, they have what's called a virtual focal point.
A virtual focal point.
It's like an imaginary point
Mhm.
behind the lens where the light seems to be coming from.
Oh, so it's like an optical illusion.
Yeah, kind of.
Where the light seems to be coming from a point that doesn't actually exist.
You got it. And just like with converging lenses, the focal length of a diverging lens, it's the distance from the lens to that virtual focal point.
Okay, so both types of lenses have focal lengths, but they act in opposite ways. Like
Yeah.
one brings the light together, the other spreads it out.
Exactly. And those opposite behaviors, that's what gives them their different applications. We've been talking about converging lenses for magnification, image projection, and stuff.
Right.
Diverging lenses, well, they have their own uses.
Like what? I'm curious to hear more about how those diverging lenses work.
Well, how about eyeglasses?
Yeah.
For people who are nearsighted, diverging lenses are often used in their prescriptions
Sorry?
because they help spread that light out before it reaches the eye, which allows the image to focus directly on the retina.
So it's like the diverging lens is counteracting that over-focusing that's
Exactly.
happening in a nearsighted eye.
That's exactly right. It's, it's a clever way to apply these principles to correct vision problems.
Yeah.
And another interesting use of diverging lenses is in wide-angle camera lenses.
Oh, that's right. Yeah. Those lenses that capture a much wider field of view.
Yeah.
Do diverging lenses, do they, like, make the scene appear smaller?
Yeah, they basically,
To fit more in?
they shrink the scene,
Okay.
allowing you to capture a more expansive. It's like having a panoramic view all squeezed onto a normal-sized image.
This is making me think, maybe diverging lenses aren't as talked about as converging lenses because their effects are more subtle.
Maybe. Yeah.
It's not always about, like, creating those sharp, focused images
Right.
that we think about with cameras and telescopes.
That's a good point. Maybe their power is in that more subtle manipulation of light,
Yeah.
It's not always about focusing, but it's about controlling the spread and direction of the light to make a specific effect.
It makes me wonder if there are even more applications for lenses.
Oh, I'm sure.
Well, we haven't even, like, thought about.
I'm sure there are tons. This field of optics, it's constantly evolving.
Oh.
Researchers are always finding new and better ways to use lenses, to manipulate light. Who knows what amazing applications we'll see in the future.
Yeah, it's exciting to think about. But let's step back for a moment, back to ray diagrams.
Okay.
You explained how we use those 3 specific rays to figure out where the image will be.
Right.
But if light is coming off of an object in all directions,
Yeah.
aren't there way more than just those 3 rays?
You're absolutely right. There's an infinite number of rays
Right.
coming from every point on that object. If you tried to draw them all, it would be a mess.
I can only imagine. So why do we only need to draw those 3 specific ones?
Well, they're not necessarily like more important than any other ray,
Right.
but they represent the overall behavior of light as it passes through that lens.
Okay.
It's a simplification, of
Yeah.
course, but it gives us the information we need to predict where that image is going to form
Right.
without getting bogged down in an infinite number of rays.
So it's like a shortcut,
Yeah.
but it's a really accurate one. It's pretty amazing that something so simple
Right.
can be so powerful in explaining how these complex things work.
Yeah, and that's one of the beautiful things about physics. We can often find these simple models that capture like the essence of a really complex phenomenon,
Right.
which helps us to understand and predict the world around us.
I really am starting to appreciate the elegance of those simple models and equations even more.
Yeah.
They may not capture every little detail, but they give us this framework
Right.
to understand these amazing optical effects.
And that understanding, that's what drives innovation.
Yeah.
That's what allows us to design new technologies and
Mm.
push the boundaries of what's possible.
You know what? It's funny. I started this deep dive feeling like I knew so little about lenses,
Mm.
but now I'm starting to see how they're truly shaping our world.
It's all about perspective, right?
Yeah.
And I think we've gained a pretty fascinating one today.
Yeah, I agree. This has been a real eye-opening experience, pun intended. But before we wrap up our lens exploration, let's take a little break. We'll be back in just a minute with some final thoughts. All right, welcome back to our deep dive into the world of lenses. We've covered so much, from the thin lens equation to those ray diagrams.
Yeah, it's really remarkable how these simple concepts can explain how we see.
Yeah, I feel like I have a new appreciation for lenses, that's for sure.
Mm-hmm.
But before we wrap things up, is there anything else from the source that really stood out to you? Anything you want to leave our listeners with?
You know, when we were talking about magnification earlier,
Yeah.
something in the source really stuck with me.
Okay.
Remember how magnification is that ratio of the image height to the object height?
Right, and we could also calculate it using those distances, negative v over u.
Exactly. And you know what I find so fascinating about that? It shows the connection between, like, the geometry and the image.
Okay, yeah.
The ratio of those distances is directly related to how much bigger or smaller the image is.
It's like this hidden math, this elegance
Yeah.
buffed into how lenses work.
Exactly, exactly. Makes you think, if these simple ratios can predict these complex optical phenomena, what other hidden connections and patterns are out there?
That's a great point. I mean, it reminds us that even in a field like optics that we think we know pretty well,
Right.
there's still so much more to learn.
Oh, absolutely. That's what makes science so fascinating. Every discovery opens up a whole new path, leads us further down the rabbit hole.
I love that analogy. We're on this, like, never-ending quest for knowledge.
Exactly, exactly. And who knows what we'll find as we keep exploring light and optics. Maybe
Mhm.
more powerful telescopes, new imaging technologies, even new ways to use light for communication, energy, who knows?
Yeah, the possibilities are endless. Well, on that inspiring note, I think it's time to bring this deep dive to a close.
Yeah, sounds good.
But before you go, one last thought. As you go about your day today, just look around. See if you can spot examples of lenses in action.
You might be surprised how much of our technology relies on these simple but powerful principles.
From your phone to the traffic lights, lenses are literally shaping how we see and interact with the world.
Keep those eyes peeled.
And never stop being curious.
That's right.
Well, that's a wrap for our deep dive on thin lenses. Hope you enjoyed it and maybe learned a thing or two along the way. Until next time, keep exploring.